Okay, let's dive right into this explainer and explore the really revolutionary concept behind US patent number 12,664,142. Welcome to the very first part of our 12-part series unpacking the fascinating architecture laid out in this patent. Right out of the gate, we're going to focus on the big picture, the vision, and introducing what's called the self-explanatory database. This is a concept that honestly challenges the fundamental ways we've built software and managed data for decades. For a long time now, the tech industry has just sort of normalized these incredibly complex systems that separate our data from our application logic. And what does that lead to? Well, software bloat, security vulnerabilities, and a massive lack of transparency. But this patent? It proposes a radically different path, a unified environment that is actually verifiable by design. So we have to start by identifying the great divide in computer science. It's known as the object relational impedance mismatch. You see, most databases rely on query languages, think SQL, right? Which are highly optimized for passive data. We can kind of think of these as our software's nouns. But on the other side of the divide, general-purpose applications rely on programming languages, like JavaScript or Python, which are optimized for active instructions. Those are our verbs. And because these two environments are totally distinct, it creates this massive amount of friction. Literally, every single time your application wants to do something with your data, you incur a heavy translation overhead. When you look at standard system designs, developers are basically forced to build three totally distinct layers: the database schema, the database query mediator, and then the application logic itself. And bridging those three layers, it requires heavy driver libraries, constant parsing, network routing between completely separate runtime nodes. It's a lot. But the hierarchical script database, or HSDB, completely eliminates that friction. It unifies execution and persistence into a single runtime kernel. It uses JavaScript as this beautifully homogeneous language for both retrieving the data and executing the scripts. The inventor of the HSDB, researcher and legal scholar Kyle McLean-Smith, actually captures this architecture perfectly with a linguistic analogy. He explains that it's as if we've been forced to communicate using nouns in one system and verbs in another. By combining an app and a database into one dynamic system, we can finally stop separating our software's nouns from its verbs. We can literally just put them next to each other in cohesive sentences and paragraphs, which allows the whole system to evolve over time in response to external events. It just makes so much sense when you think about it that way. So the absolute crucial point here is code data locality. That's the architectural goal of merging the application layer and the database layer so they execute securely as one isomorphic entity, meaning they share the exact same shape and structure. Instead of data just being this passive placeholder that some external application acts upon, the data and the instructions to manipulate that data live together natively in the exact same hierarchical tree structure. Moving right along, let's get into the self-explanatory database visualizing U.S. Patent 12,664,142. Let's actually look at the patent schematics to see how this all clicks into place. Notice how JSON data structures exist seamlessly within the hierarchical file system address. We're seeing data properties, in this specific case it's quiz questions and answers about the distance of the moon from Earth, stored natively right at this node address. This is the passive user data perfectly and cleanly organized in a parent-child relationship. But look at what happens right alongside that data. At the exact same path address, the system embeds active JavaScript modules. You can literally see functions like isAnswerCorrect and parent co-located directly with the JSON data. This is visual proof of what we mean by self-explanatory nodes. The database doesn't just hold the information, it contains the exact logic required to operate on it. The node itself knows how to answer the question. No need for a separate external application to process it whatsoever. And stepping back a bit to look at the broader computing environment where this single unified kernel runs, by combining the data and the application logic inside a single interpreter environment, the patent creates a highly transparent system. It fundamentally removes that whole trust me posture that developers so often have to take with complex three-tier architectures. Because the code and the data are unified and co-located in this hierarchical format, lay stakeholders, people without any deep database expertise, can easily peruse and verify the application's behavior. Next, let's explore the math of unification, Pythagorean model. To make this infinite stacking of nouns and verbs actually function without, crashing the whole system, we have to look at the deep mathematical underpinnings. Because you can't just throw code and data together blindly. They need a really solid structural scaffold. The HSDB architecture relies on a mathematical framework referred to as Pythagorean model. Now, this concept treats code, the action, and data, the object, as completely interchangeable entities. It models data and execution as a non-halting, self-reproducing automaton. Essentially, that's a system that continuously loops and builds upon itself without ever needing to stop and fetch new instructions. It takes the non-halting property of a right triangle's diagonal from classical Euclidean geometry and brilliantly applies it to software architecture, pairing finite modulo sequences for iteration with infinite number line sequences for recursive structures. The real secret sauce here lies in the scale symmetry base exponent. That's essentially c minus b over a, all to the power of n. By utilizing this specific recursive coordinate system derived from a right triangle, the code's execution path and the data's retrieval path become exactly the same thing. The math generates these beautiful, scale-symmetric geometric patterns that serve as unique coordinates for the data structures, linking all the way back to the Fibonacci sequence and the golden ratio. It mathematically proves that the program and the data are structurally isomorphic. Now, let's jump into a comparative analysis of hierarchical database implementations. To really grasp just how radical this total coupling of compute and state is, let's map out how it compares to other ways the tech industry has historically nested data and instructions. When we contrast SeedTreeDB, which is the commercial name for HSDB, against other prominent hierarchical implementations, the differences are pretty striking. For instance, you can see AI systems like Thought Treasure using conceptual hierarchies to simulate human reasoning and reduce search spaces. Then you have systems like the DelFFUS scenario and script database, used in hydraulic simulation, which nests scenario directories and scripts. But check out the key architectural advantage of HSDB. By putting a native JavaScript application directly inside the database kernel using that fractal coordinate math we just talked about, only HSDB solves the object relational impedance mismatch entirely for general-purpose software. It's not just simulating an environment, it's a unified state engine. Okay, moving on to Back to the Future, the historical precedent. As novel and advanced as this patented HSDB math is, the core concept of integrating a database directly into a programming language actually has an incredibly proven, if sometimes forgotten, lineage. A truly surprising fact is that this architectural convergence dates all the way back to 1966. Yeah, long before modern NoSQL or serverless cloud environments, researchers at a Boston hospital, Massachusetts General Hospital to be exact, had a radical insight. They desperately needed doctors and nurses to concurrently access and update patient data in real time, and they had to do it on hardware that had only 8 kilobytes of memory. So, to solve this impossible problem, they created MUMPS. This was a programming language that natively contained a schema-free, hierarchical data model, which perfectly mirrored how a patient has lab records, which have results, which then have values. In MUMPS, variables and database nodes use the exact same syntax. It successfully integrated passive data and active commands to manage massive multi-user clinical systems without any of the modern software bloat we're so used to seeing today. It absolutely proved that unifying the language and the database is not just possible, but incredibly resilient. So resilient, in fact, that MUMPS-based systems still serve the vast majority of US patients today. So, to wrap up our explainer today, I want to leave you with this final, somewhat provocative thought about the fundamental nature of how we build software. If computation, our verbs, and state, our nouns, are mathematically and historically proven to be naturally isomorphic, why did the tech industry ever force them apart into such complex, separated layers in the first place? As we continue our 12-part series on this patent, really keep this question in the back of your mind. Because as we'll see, this self-explanatory database proves that putting them back together might just be the entire future of computing.